cannot reflect all our feelings. It's impossible. But a little bit, a first approximation about how we are changing in our moods, in our feelings, in our ability to be risk-friendly or to reject. Dear friends, I would like to finish now. I know it's now morning in Medan. Maybe some of you are a little tired already, but please remember there was a person who spoke to you on chocolate. It was mathematical chocolate. And he spoke to you about sentimentality. You know, sentimentality. For example, as you know, dear students, the husband of Professor Queen, Professor Professor Queen, he sends me beautiful photos of West Sumatra. So he sends me photos from West Sumatra because they are beautiful waterfalls, right? West Sumatra, beautiful lakes, beautiful mountains, beautiful people, beautiful waterfalls. And so he's very, very romantic. He's sentimental. But we have to use mathematics to make it useful for us, to make our feeling, how we are, useful in order to tell how it relates to our world of finance, of business, of management, and so on. So thank you very much for listening and accepting my chocolate. Thank you very much.
Yeah. Thank you very much, Professor Gerard Willem Weber. Thank you for your presence.
You're welcome. You're welcome.
The next for Buchu Gurbus, PhD. For Buchu Gurbus, please, this is the time for you. Where are the
Yes, I am here.
Presentation. Please.
Yes.
The time for you, Miss Buchu Gurbus, PhD.
Yes. So here, thank you. I thank you very much for your organization and for being able to talk here in the event. Can you hear me?
Yeah.
Yeah, I hear.
Can I share my screen? Is it possible?
Yeah, I will make you make
I
a
hear.
Okay, I will arrange.
Hey.
I see you.
Okay, so do you have my slides?
Welcome.
Can I share? I hope you are all well. Thank you for your opportunity to talk here in the event. It was very nice to see you here.
Yeah.
But do you have my slides?
Yeah,
I cannot share the screen.
Yeah, you can share the screen because I make you to make a co-host now. You can share now.
Okay, so you are going to share the slides?
Okay.
So I'm a postdoctoral student in Johannes Gutenberg University of Mainz in Germany. And also I'm an assistant professor in Üsküdar University at the Department of Computer Engineering in Turkey. Today I would like to talk about a mathematical technique in order to solve a specific type of problems. So here in my talk is the overview that you can see. I will give you a brief introduction about the technique that I consider the solution, because we already know that it is solving the problems approximately. It is important because solving the problems is important in our lives. So where we improve a technique which is based on orthogonal polynomials, and then we generalize it for typical matrix problems by using error analysis to show you the efficiency of the technique. And there will be some examples to give you an applicability of the technique. So here is the problem that we deal with. It is called as the pantograph type functional differential equations. So here we have the problem, as you can see here. And this is mainly for solving this type of problems we consider as a hybrid, proportional, and variable delays. If you already know, we have some problems in our life, so we would like to solve it immediately. So this is the idea here, that we can consider this pantograph type differential equation. And also we have some mixed conditions. For example, in the beginning of problem, we have some conditions that we are inside, and then we would like to approximate it in order to get at least a little solution. So this is a point-wise conditions that we can here see, the points A and B. And we have some variables here, which are considered as the proportional variable delays. It's another function inside of the unknown function here. And then we have the limits of these variables here between positive intervals. So here, this type of problems are very helpful in order to understand some real phenomena, which is including the functional differential equations, the name of this type of differential equations we consider here. And they are very useful in many fields, such as in chemical reactions, and also some mathematical biological models, in economy, in elastic mechanics, and so on. So as you can see here, we have a variable, which is the variable here, and also we have some difference in the time variable. So on the other hand, these type of problems are not very easy to solve. So that's why we use some numerical techniques in order to get the approximate solutions. So these are the very popular numerical solutions that you can see, Runge-Kute, and also some multi-step methods, some collocation methods, which is going to be based on this study, and also some behaviors of this type of equations by using stability and the asymptotic behavior, and some oscillations are very important on such of problems. So the idea here is about using a numerical method in order to get the solution of this type of problems. And we consider a generalized Laguerre series in order to get the approximation for our unknown. Because as you remember, here we have the unknown in the problem, and we would like to know what is this y in the end. So that's why, in order to find this unknown, we have an approximation by using these Laguerre series. They are called as the generalized Laguerre series because we have the variable and also one alpha parameter inside. So this is the Laguerre series we define here in the equation. And also we would like to find the solutions of this problem by having some point-wise results for XR. So these XRs can be defined here in the form 4. We call this one is in the standard form because, as you remember, it was our interval by having the AB, our variable. So that's why we can find the solution point-wise in this interval by using these standard collocations. And also we can consider the Chebyshev-Lovato collocation points in this form to get the results point-wise. So for each XRs, we consider a polynomial approach. They are in Laguerre polynomials. And the generalized Laguerre polynomials generating function is defined here in equation 5. So these are the generated functions which are useful for finding these ln values. As you remember, these are the guys that we are interested in order to find the approximate solution in the end. So they are very helpful to get this approximation. Here we have the relations. And in order to solve this problem, we consider a matrix approximation. So as you remember, we have the problem in equation 1 and 2, and we would like to find an approximation. So here in this approximation, we have the Laguerre series in generalized form and also unknown coefficients. So here generalized Laguerre series can be written in a matrix form, and these are the unknowns. And also we will get an help for representing our ln values, ln matrix, here in equation 8. So these are the ones that we can use in the formula here in 8. And also we have a specific matrix here, M alpha, and this alpha, as you remember, was the parameter we were having inside of this Laguerre generalized Laguerre form. So here I would like to find this approximation by using the relation previous here 7 and 8, and I construct this 9. Also, as you remember, in our problem we have the derivatives. As you remember, this sign is the derivative of the unknown function. So I already write here the matrix form of the unknown, but I also need its derivative, right? But it's missing here. So that's why I need to consider some relations between the derivatives of the matrix here. And we will get some help from this matrix B in order to construct this relation here in equation 11. And besides, as you remember, we have some functional terms inside of our function instead of only x. So these are the arguments inside of our equation. So I need to adaptate my matrix forms here by using the different form of this x variable. So instead of x, I need to consider these relations here, and they can be written here in the matrix form, equation 12, where I use some specific matrices in order to define this x. And then now I complete by having the derivative and the variable as the functional arguments, as you can see here. So this is the matrix equation we can define. And in order to have the system of matrix equations, we can consider now the collocation points. As you remember, we would like to get the results as pointwise. So here we already defined the collocation points. So these XR values are the collocation points we define. And we just replace here inside of this matrix relations. Then we can write simply this equation in the form 14. But here we extended the dimension of the matrices in this form. So then we have these relations in a higher level, as you can see here. And then we construct the system of matrix equation here in equation 15. So we have the, we also have the conditions here in the problem. So that's why we also need to consider the matrix relations of these conditions. So if I apply the similar technique for our conditions matrix, can be found here in this form. And this is the one that we need to replace in our system. As you remember, it was our system for the solution. I would like to find these unknowns in order to get the approximation. So now it is time to replace by using these conditions at the end of constructing new augmented matrix. So if we have this relation, the rank relation between the system and the W matrix, there we can solve this system by using some methods such as Gauss elimination or some other techniques to get the unknown matrix A. Just after finding these A coefficients, we can replace in the series form, as you remember here. Then we can get the unknowns, the approximate solution of the problem. So, but we are not sure if the problem is very close to the exact equation, or if we have an approximation which can be said as very well. So in this case, we need to apply some error analysis technique. If you already remember, there were some approximations can be defined by using the discretizations, and also we can use some error techniques in order to see this kind of numerical methods are useful or not. And we can get some help from the calculus theorems. I don't know if you remember the mean value problem here. There we can also use a residual correction in order to get a better solution for such numerical techniques approximations. So let us consider our differential equations with Rn. And let's see that if we have this approximation here, it is very close to 0, because I would like to find the result is very close to 0 when we have the difference between the exact and the numerical solution. Because if I have the solution which is very close to the exact solution, then we can say that it is very useful technique, and we can get the efficiency from as much as our problem. So this theorem helps us with the relations here, which means that if I have this, the residual function is very close to 0, and having these relations, then we can say that the approximation is well enough, and this Rn of x approximating to 0 whenever we have these n values are large enough. So let us consider these results to see the application of this technique. So here I use the computer programs. They are very useful. Computer programs are very useful to get these such solutions. And as you remember, I have the form of the differential equation here in this form. What was that? As you remember, we have the unknown function here, y of x, and we have a function inside of this variable with the first derivative, and here is the second derivative we have, and we call this part as the g of x function. And also I need the conditions here, and the conditions are given at the point 0. We have -1 and 0 for its derivative here as two conditions, because we have two conditions here. What is the reason? Because here we have the second derivative. In order to construct such problems, we need to have the same number of conditions as the derivative of the function. So we call this function, this differential equation, as the pantograph type functional differential equation. And we have the initial conditions here because we have only one point, which is starting with 0. Whenever I have the approximation by using the numerical algorithm, I will have these results. As you remember in the beginning, we have these Laguerre series solutions. Here in this form. So there is an n. I can extend my series solution whenever I like. So here we need some specific extension values, and we call these guys with the capital N. So in the end of these results, I consider different numbers of n values. And then, as you can see here in the picture, whenever I have this higher number of n values, which is approximating to exact solution. So this black one is the exact solution of the problem. And if I have n values large enough, it's approximating to the exact solution, as you can see here. So also here here we can see the absolute errors, which means that the difference between the exact solution and the approximate solution. Here, as you can see, it's getting smaller because here we have the n value as 30. So it is very close to the exact solution, as we remember from this picture. And then the difference getting smaller. When I have the n value as 2, here is the error. As you can see, it is larger. And then if I have n value as 5, it is in the middle. And if I have 30, it's getting less. So it's decreasing, as we can also understand from this picture. So when you compare these three guys, you can see that we have the better approximation whenever we have this n value is larger. As a second example, we also have this unknown function with the arguments exponential here, and also here with the third derivative. And then here we have the proportional variable for the first derivative. And as you can see, we have the third derivative with the three different conditions here. And we know the exact solution of the problem is exponential minus x. So here we compare some different techniques with the same problem. And as you can see, we have the approximation with the Taylor collocation method, which is another technique. I use these Laguerre polynomial solutions here with this abbreviation. And I use different n values. For example, here we have the n values as 5. As you can see, we have this. These are the absolute errors of our problems when I have n as 5. So this is the solution with Taylor collocation, and this is the solution with the improved novel technique by using the generalized Laguerre polynomials. So here we have the results. And as a conclusion, these type of problems are very difficult to solve if I consider some analytical techniques. Analytical techniques are the ones that we can solve the problems with regard to some theoretical background, but also we can use some numerical techniques in order to get the approximate solutions of the problems. So most of the time we consider these results in an interval where we define our parameter, and then we can have the approximate solutions pointwise mostly, and then we can improve the technique, or we can change the problem, or we can see the application in the real world. So for such problems are very important, especially in biology and also in economical background, because we can change the variable. We cannot say that all the time we use the same variable. We can change it a bit, and it makes very huge difference in such problems. So that's why they are very useful to understand the real world phenomena, and it can be extended to other studies. And it was the time that I got some foundation from the university's department, scientific research projects. And these are the references. Thank you for your care and attention. So this is all for my talk here. If you have any questions.
Thank you.
Thank you.
Thank you. Thank you. Good you.
Thank you. If you have any questions.
Presentation. How are you?
Fine, and you? Nice to see you all.
Maybe I can say something.
Thank you very much.
Maybe I can say, because Mrs. Burcu, Professor Gürbüz, she helped us a lot. She helped in a project with Professor Herman, Dr. Smile or Smiling Face, we call him a Smiling Face, Dr. Ismail, and me. She has done a great work because similar techniques that she showed in her presentation also apply in the dynamics of what we call rumor propagation, right? So
Yeah.
when I spoke about sentiment, one form, one articulation of sentiment is rumor. That's the communication side of sentiment. Some part of it is called rumor propagation. And my friend Selma Belen, she's one of the organizers of that whole worldwide study. And Professor Gürbüz strongly contributed to this field with us, but she was the main author, are based on the techniques like those that she presented to us today. So thank you very much, Professor Gürbüz.
Thank you too. It was very nice to see you now.
Okay, thank you very much for your coming in this meeting. I hope this meeting will be continue maybe. And after that we will join in the Simantap seminar, right? In November. Maybe there is any question from the audience maybe? Ada beberapa pertanyaan yang mungkin tanyakan sama audiens. Kalau bisa biar kami bantu untuk terjemahkan. Kalau ada pertanyaan.
Professor Ismail, Professor Queen, maybe I can say I liked it. Many young people sent comments. So the chat was used by many young people. So this shows that the students are very intelligent and very kind. So I have to say that many of your students are very kind, which means friendly, and also smart, because they give a response to the talks. And of course, talks sometimes a little difficult for young people. So many of them were very friendly and they expressed good emotions, good sentiments in the chat forum. So thank you very much to the young people of Indonesia.
Yes.
Maybe they miss chocolate from you when you come to Medan. Okay. Any question from audience? Ada pertanyaan?
Professor Smiling Face.
Yeah,
as
a committee,
I can make an addition because Professor Gürbüz knows it very well. We are going to have 2 conferences in the next year. We don't know whether they will be online or offline, on the venue or off the venue. And one is called IFORCE 2021 in Seoul, in Korea. Korea is like Gangnam Style. You know Gangnam Style?
Gangnam Style.
Riding a horse and listening to music. So this is called Korea. So this is next year, IFOS conference in Korea. And there's another one, which is 2 months earlier. This is called Euro Conference, Euro 2021 in Athens. Athens is called Greece. It's the capital of Greece. Greece is a country of huge culture, and it's very closely related in history with Turkey, where Professor Burcu is from. She's from a city which is close to Greece, very, very similar food and dances. So we have a conference in Athens. It's called Euro 2021. And we have a conference in Seoul, which is South Korea, next year in summertime. So Professor Queen and Professor Herman and Professor Smile or Smiling Face, they know about it, and they can give young people and the experienced scholars more close information about it. Professor Herman, also Professor Gürbüz, also stream organizers. Also Professor Suryati and others, they are stream organizers. And anybody or everybody who would like to help us is kindly invited to contact us. So thank you very much, dear Professor Queen and Professor Smiling Face.
Yeah, okay.
Thank you very much.
If nothing.
Terima kasih.
Any question? They are very surprised by the presence of such the great keynote. Thank you for your coming to this meeting. I hope this meeting will continue. As you all know, our keynote today is very important, maybe, and have a lot of schedule, but they are willing to spend time with us. and we can say thanks to all parties and see you in the next event. Maybe you have a close statement from the Professor Burcu and Professor Willy to motivate our students to respond to the mathematics what the actual now in your country or the other world in this world.
Thank you for Professor Willy and Professor Bulchu. I hope this event will continue at the next meeting, at the next event. I know that this event is very, very interesting, very, very useful for me and for all of this present. Thank you. Because the time is over, we have the other activity. So that presentation by Dr. Ismail is postponed. Let's get the close this event. We'd say Hamdalah. Alhamdulillahirabbil alamin. Thank you for all of you. Thank you. Thank you.
Thank you very much, dear professors and chocolate professors. Thank you very much, dear professors and chocolate professors.
I remember
chocolate.
You get chocolate for me.
Yeah.
For person in Winsu. Thank you.
Bye-bye, Professor.
Thank you.
Bye-bye.
Thank you, Prof.
Thank you,
Burcu.
Professor Burcu.
Thank you. Thank you.
Thank you. Bye-bye.
Thank you. Good
Bye-bye,
day.
chocolate
Bye-bye. Bye.
professors. Bye-bye, chocolate
Thank you.
professors. Bye-bye, chocolate professors.
Thank you.
Congratulations. Congratulations. To the successful conference. Congratulations.
Si mantap.
Yes, yes.
Bye-bye, Professor.
Bye. Bye-bye.
Professor Chocolate,
Bye-bye,
it's
chocolate
very nice to
professors.
know you.
Meet you the time. Meet you time. Pak Ismail nggak di foto Pak Ismail. Nggak di foto pesertanya Pak Ismail.
Tangan tanya Pak. Mas ini the end.
Manis nih, buat aku jadi terngiang-ngiang, hei. Jadi gimana? Suka sama lebih dewasa. Ngapain di sini? Udah. Ini yang kusuk. Gue kirim link absen mana dia? Terus mau tidur? Mau tidur? Ambil bentar deh. Doraemon. Baru ganti ya. Kayak mana isinya? Aku. Kerupuknya yang beri ya. Yang kerupuk hitam ya.
kira quite